OCR A level chemistry, module 6, part 1. This goes up to and including esters, and then everything else will be in part 2. So, as we discussed in module 4, an aromatic compound is any compound that contains a benzene ring, which looks like this. You can draw it either of these two ways, but I much prefer the one on the left hand side, and we'll discuss why later. The spec says that you have to be able to describe the difference between the benzene model and what they call the Kekulé model, named after the guy who made it. The Kekulé model has an alternating C-to-C double bond, whereas the benzene model we say is delocalized, and we'll get onto that more later. Kekulé will decolorize bromine, the bromine water test for alkenes, whereas benzene doesn't. In the Kekulé model, there are two different lengths for the C-to-C bond and the C-C bond, whereas in the benzene, all bonds are 0.139 nanometers. And finally, the enthalpy for hydrogenation of the Kekulé model is 3 times the hydrogenation value for cyclohexene, whereas for benzene, it's slightly lower. Now, benzene is planar and it is cyclic, and 3 of the 4 carbon electrons are bonded to other carbons, and then 1 is obviously bonded to hydrogen. And these hydrogens are at 90 degrees to the carbon. This is how you draw a 3D model of benzene. So you draw a flat hexagon, and then you have to make sure you draw your p orbitals, which are peanut shaped. Remember, that's how you remember it. And then you do the sideways overlap of these p orbitals, and that is your pi bond. And because there are pi bonds all the way around, we call this model delocalized, like we said earlier, and all that means is electrons could be anywhere within that ring. Naming conventions. When you have an alkyl group on your benzene, you say the name of the alkyl group, and then you say benzene. And make sure you include any numbers if you've got multiple, and obviously put them in alphabetical order if you've got more than one. When you have a halogen attached to your benzene ring, you do the same thing. You say halogeno benzene, chloro, bromo, iodo, whatever. Now this is a new group, you won't have seen this before. This is NO2, also called nitrate. And for this, you're going to put the prefix nitro in front of benzene. Now, with groups that take priority for the suffix, you're going to use the prefix phenol. So in this example, because it contains a ketone, ketone takes priority, and so we're going to say phenyl ketone, in this case ethanone. Now there are exceptions. This here is benzoic acid, and notice how you can't have the carboxylic acid functional group on the benzene ring. You have to have it on an extra carbon, because you can't triple bond to a benzene ring. It doesn't work. Rather than aminobenzene, this is phenylamine. Just a quick note from future me editing this, I say aminobenzene quite a lot in the next bits of the video. I'm wrong for saying that, and I'm very sorry. Rather than benzonal, this is benzaldehyde. Just to clear up on this numbers thing, this is methylbenzene. This, however, is 1,4-dimethylbenzene, because 1 is at position 1 and 1 is at position 4. And in this one, 1 is at position 1 and the other is in position 2, because you start at where the first group is, and you keep that locant number as low as you can. So this is a new mechanism, electrophilic substitution, and what it's saying is you take your benzene, you chuck it in an electrophile, and then you get your electrophile on your benzene ring and a hydrogen ion. This is an example of electrophilic addition. Here we're forming the nitrate group, and we do this with sulfuric acid and 50 degrees. And the reason we do it at 50 degrees is to avoid further substitution. Now, you have to use concentrated acid for it to work. That's concentrated nitric acid and concentrated sulfuric acid. So, if you're asked to draw the mechanism in an exam, you may be asked to draw how the electrophile is generated, and that's step 1 here. So your nitric acid creates your nitrate ion, H2SO4 loses a hydrogen, and then water is also formed, and your nitrate ion is acting as your electrophile. Now, step 2 occurs like I've written it. That is your actual mechanism, and you can tell because of all the curly arrows and things, and it forms an intermediate, so you may be asked to draw that intermediate, and then you may be asked a question on why sulfuric acid is a catalyst, and that's because the H plus ion reacts with the ion of sulfuric acid to regenerate sulfuric acid, and so because it's regenerated, it's a catalyst. Halogenation of benzene, we say that it's formed in situ, and you need to use something called a halogen carrier. Now you can either use aluminium or iron, it doesn't matter. I choose to use aluminium just because it makes my life easier. The mechanism is still exactly the same as it was for nitrate. You can alkylate benzene like this, and again you're using a chlorinated haloalkane and a halogen carrier, otherwise it won't work. This is called the Friedel-Crafts reaction. Alkylation is when you make your benzene ring into a carboxylic acid, and an acyl group is like a carboxylic acid, except instead of the OH group, it's got a chlorine or a halogen on it. Like I said earlier, benzene is delocalized, whereas a double bond is localized, and the pi bond in it is very electron dense, and this means that it's very reactive. And another exception to the naming rule earlier is phenol, but we're going to go into a lot more detail about phenol than we did for the other ones, and phenol is just OH bonded to one of the carbons in the benzene ring. So things like phenylethanol are not phenol, only when it's bonded directly to the benzene ring is it phenol. Now, phenol acts as a weak acid, and so it can set up an equilibrium, but it's nowhere near as acidic as carboxylic acid. Phenol reacts with sodium hydroxide, ethanol doesn't, and so this is the test for a phenol group rather than a alcohol. But how do you distinguish between carboxylic acids and phenols if they're both acidic? Well, you can use sodium carbonate, which will not react with phenol at all, but will react with carboxylic acid. And phenol, unlike benzene, does readily decolorize bromine, with no need for a halogen carrier. It also reacts with dilute nitric acid to form either 2-nitrophenol or 4-nitrophenol. And we'll discuss why that is in a little bit. Now, the reason phenol reacts more readily with things like dilute acids or halogens without halogen carriers is the two lone pairs from the oxygen delocalize into the benzene ring, which makes it more electron dense and more ready to react with electrophiles. So we say that OH is an activating group because it makes the benzene ring more reactive, and we say the same for an amine group. We say the opposite is true for a nitrate group. We call it deactivating, and it makes it less reactive. Depending on whether it is an activating group or a deactivating group, it can change where the next group is substituted onto the benzene ring. So you need to know these ones for your exam. Amine and hydroxyl group are 2,4 directing, and nitrate group is 3 directing, and I'll show you what I mean now. Now, if we have nitrobenzene and we want to chuck a bromide ion on there, we know that the nitrate group is 3 directing, so the bromine is going to substitute onto the 3rd position of the benzene. Whereas with an amine group, it's 2,4 directing, so adding a bromide ion can either go on the 2nd position or the 4th. The directing groups affect the order of synthesis, and I'll explain what that means here. So we want to make 2-nitrophenol. How do we do that? So if we start with nitrobenzene and we try and add a hydroxyl group on, well, it's not going to work. Nitro group is 3 directing, so when you put the OH ion on the benzene ring, it's going to go to position 3, and that's not what we're looking for. Whereas if we start with phenol, which is 2,4-directing, then we get that product. Although it's important to remember that you only get 50% yield because phenol is 2,4-directing. So some of the product, we're going to guess about 50%, is going to be what we're looking for, and then the other 50% is going to be 4-nitrophenol. So moving on from benzene, we're now looking at carbonyl compounds. And as we've said before, you can oxidize an aldehyde, which is the one we have here, to form a carboxylic acid. Now to do this, you use acidified dichromate. In this case, I'm using potassium dichromate. You use H2SO4, and you make sure you're doing reflux, which again we've talked about in module 4. And just a reminder that this double bond is the overlap of p orbitals and the sideways overlap of p orbitals, but it is not an alkene. And oxygen is more electronegative, so the electron density lays closer to the oxygen. And that electronegativity means that it reacts really well with nucleophiles. Now, you can change an aldehyde back into a primary alcohol by reducing it with a reducing agent. We're going to represent our reducing agent with an H in square brackets, like we represent our oxidizing agent with an O in square brackets, and the reducing agent we're going to be using is NaBH4, which I've written there. And you can do the exact same with ketones to form a secondary alcohol. So when you reduce an aldehyde, you always get a primary alcohol, and when you reduce a ketone, you always get a secondary alcohol. You can react an aldehyde with hydrogen cyanide using sodium cyanide and sulfuric acid as your catalysts to form a hydroxynitrile. Because you're adding a carbon, you're extending the chain of your organic compound. We do this through nucleophilic addition, and this is another mechanism. So in the first part, you're reacting to form a negative intermediate, and then this negative intermediate reacts with your water to form your alcohol and a negative oxygen ion. So the same happens when you add cyanide. This is what the mechanism looks like simplified. This is what the full mechanism looks like with hydrogen cyanide. You can test for carbonyl groups with 2,4-DMPH, also called Brady's reagent, and it will turn an orange solution into an orange precipitate if a carbonyl group is present. But then how do you differentiate ketones and aldehydes? You do that through Tollens. Now, Tollens reagent is also called ammoniacal silver nitrate, but honestly, just remember Tollens reagent. Make it, you're going to add silver nitrate, then you're going to chuck in some sodium hydroxide, which will form a brown precipitate. Then you add dilute ammonia, and it changes it to a colorless solution. Then you take equal volumes of unknown solution and your Tollens, and you heat it to 50 degrees for 10 to 15 minutes. And if there's a silver mirror, then you have an aldehyde. So the silver is reduced and the aldehyde is oxidized. You can check the purity using a melting point apparatus to compare the melting point to the known value. So for carboxylic acids, the naming convention is you take the E off the alkane and you chuck oic on the end, and then obviously acid. Now, carboxylic acids can form hydrogen bonds either with water or with themselves. But this only works for carbon chains under 4, because otherwise there's too much surface area for induced dipole-dipole bonds, and that becomes the strongest attractive force. But as long as they're 4 or below, then they're very soluble, and so they create weak acids, which you can see from the equilibrium here. Because it's an acid, it neutralizes with bases and redox reactions with metals. Now, when we take the hydrogen away, we call it a carboxylate group, and this will be important when we do esters in a bit. So when you react ethanoic acid with magnesium, you create magnesium ethanoate and hydrogen gas, like you would with any other acid. And reacting ethanoic acid with a metal oxide gives you the salt and water. Reacting it with a base gives you the salt and water, or you can just write it as an ionic equation to form just water. Reacting with a metal carbonate gives you the salt H2O and carbon dioxide, and this is the test for a carboxylic acid as opposed to phenol. That leads us on to our next functional group, which is an ester that looks something like this. And we name carboxylic acids after, first of all, the alkyl group, which in this case is propyl, and then the carboxylate group, which in this case is ethanoate. You react an acid and an alcohol with concentrated sulfuric acid at 80 degrees to form an ester and water. You can also use acid anhydride, in this case we're using ethanoic, which looks like this, with an alcohol to create an ester. But rather than water, you form the carboxylic acid of your ethanoic anhydride. So in this case, ethanoic acid. But if you're using propanoic anhydride, you'd form propanoic acid. You can break down an ester by hydrolyzing it, and you do this with water under a heated reflux and with diluted acid. And this creates your carboxylic acid and your alcohol. And with a hot aqueous alkali, you form the carboxylate salt and the alcohol. You can react a carboxylic acid with SOCl2 to form an acyl chloride, sulfur dioxide, and hydrogen chloride. And like I said, the drawn structure on the right hand side, or your product side, is what we call an acyl chloride. You can use acyl chlorides to form esters with alcohols, and this works particularly well with phenol because phenol won't react really with carboxylic acids. Reacting an acyl chloride with water gives you back your carboxylic acid and hydrogen chloride. So, acyl chloride you can react with excess ammonia to form a primary amide. You can form a secondary amide by reacting an acyl chloride with a primary amide. Like normal hydrocarbons, you can have aliphatic amines or aromatic amines, aromatic obviously containing benzene rings. Now, like I said earlier, you can have primary amines, secondary amines, or tertiary amines. And normal naming rules apply to this. So if you have two ethyl groups on a secondary amine, then it is diethyl amine. So a little bit of a nuance here. When an amino group is on the end of a carbon chain, then it goes alkyl group amine. But when it's in the center, it becomes amino propane in this case, or amino whatever your carbon chain is. Now, in terms of basicity, this is what it looks like. Tertiary is more basic than secondary, secondary more than primary. Primary is more basic than just ammonia, and ammonia is more basic than aminobenzene. If you have two or more different groups, you use the letter N in front of the smallest group and then the next small group. Now, you can create quaternary amines, and this works off a coordinate or dative bond, and it creates a positive ion. Reacting an amine with an acid gives you a positive ion and that negative ion from the acid. And likewise, you can do the reverse, so you take a chlorohydrocarbon and you react it with excess ammonia to form a salt. And you can take this salt and react it with sodium hydroxide to form an amine, sodium chloride, and water. And it recreates that primary amine. Reacting a haloalkane with an amine gives you a secondary amine. And if you want to create a tertiary amine, you can just use a secondary amine rather than a primary amine. Now, creating aminobenzene is slightly more difficult. You have the nitro group, you have to start with the nitro group, and then you have to reduce it. And you're going to do this with a tin catalyst and concentrated hydrochloric acid, and then the second step, you're going to add excess sodium hydroxide. We're moving on to amino acids, which you can tell gets its name from the amine group and the acid group, which I've done in their respective colours there. You can react an amino acid with hydrogen chloride, and that will give you this. And this is a salt. And obviously, as it is an acid, you can react it with a base to form a salt and water. Now, reacting an amino acid with ethanol and hydrogen ions will give you an ester and water. And this can, in some cases, form amides, which are like amines, except they're attached to a carbon that's double bonded to an oxygen. And just like amines, these can be primary, secondary, or tertiary, depending on the number of hydrogens attached to that nitrogen. And like with amines, you're going to use the letter N for the small group, and then you're going to go to the larger group, except you're going to always use the molecule with the carboxyl group as your final one before the amide. So if we were to swap out that methyl for a propyl group, it would still be N-propyl ethanamide because the ethyl has the C double bond O in it. In the Module 4 video, we talked about EZ isomerism, and those are examples of stereoisomers that have the same structural formula but a different spatial arrangement. And now we're going to look at a different type of this called enantiomers or optical isomers. Now, these need to contain a chiral center, which is a carbon attached to 4 different carbons. And what this does is it creates 2 non-superimposable mirror images. So we're going to mark any chiral centers we have with an asterisk. I've done mine in red here, so you can know what I'm talking about. And you can see here that amino acids have chiral centers. A lot of them do, except for one. And that means that they show a lot of enantiomers. Now, you need to know how to draw them in 3D so you can represent enantiomers properly, because they might ask you in an exam, draw the enantiomers of such and such a molecule. So you draw them like this. You can see we've got the 2 solid wedges facing each other and the 2 dashed wedges facing away from each other. So, for the last part of this video, we're going to be talking about polymers, and we're going to start with polyesters. Now, there are 2 ways to form a polyester. You can either use a molecule that contains both a carboxylic acid and an alcohol, or a molecule that has a dicarboxylic acid group and a dialcohol molecule. Hopefully you can see from here where we get the name condensation polymerization from, and that is it forms water and the polyester. And this is an example of a molecule with both an alcohol and a carboxylic acid group, and it reacts to form this polymer where the repeat unit is at the bottom in the brackets. Now here is an example of a dicarboxylic acid and a dialcohol, and again you can see where the water comes from for this to be a condensation polymerization, and it forms this repeat unit at the bottom here. And for polyamides, it's almost exactly the same. You can either have a molecule that contains both carboxylic acid and amine groups, or you can have a diamine and a dicarboxylic acid. So here you can see where the water comes from, and this is the one with an amine group and a carboxylic acid group, so it creates a smaller repeat unit, which you can see at the bottom here. So this one here, on the other hand, is the one with a dicarboxylic acid and a diamine. And you can see again where the water comes from, and it creates a longer repeat unit. Now you can hydrolyze polymers to recreate your reactants, and you can do this either with a base or with an acid. And using a base will reform your alcohol, but it will leave you with the salt of your conjugate base, so it will form your carboxylate group and then the positive ion from the base. whereas using an acid gives you exactly your alcohol and your carboxylic acid back. And the same can be said for hydrolyzing polyamides. Using a base gives you the salt of the conjugate base and your amine. But using an acid gives you your carboxylic acid, but it also gives you your tertiary amine, which is not what you started off with. So that's it for part 1. Next part will include carbon-to-carbon bond formation, NMR, and synthetic routes. I really hope you enjoyed. Thank you for watching. I hope it helped in some way, shape, or form, and I will hopefully see you next week. Thanks. Bye.